Compressive sensing made quite a splash in recent years, which is why I want to talk about it. Intuitively, it's about the following. Oftentimes, you acquire an image densely. So this is standard, right? You make one measurement per pixel and get a complete image with millions of pixels. You then compress it in a lossy fashion so that it won't eat up quite as much space on your hard disk. And well, if you want to look at it, you decompress it again. And the basic idea of compressive sensing is that if it is possible to compress images, then there should be a way of not spending quite as much effort in acquiring these images, because apparently the images are simple in some domain, or else compression would not be possible in the first place. So in a way, you want to acquire the image directly in the compressed domain. And that works as follows. I'm starting with a formula and we'll then try and give some insight. So we want to find an estimated image X. Such that this image is sparse in the L1 sense in some space. So this is a transformation into a space in which the signal is sparse. And you want the whole thing to be close to the observed data, of course. So you can say that some measurement no, wrong, excuse me. These are the observations, and yeah, this is my measurement matrix. I need it here. Is smaller than some user chosen threshold. So delta is supplied by the user. Now phi is a measurement matrix. So let me give two examples. So let's say example 1, my measurement O, let's say, is a very smooth function. Now the traditional way, which we don't want to follow now, of acquiring the signal would be to measure it at each and every location. So for n pixels, we need n measurements. Now the idea here is to instead use some simple, so let's say not O, but let's call this the signal of interest. Now the idea here is to measure not the entire signal, but a projection of the signal onto some measurement basis function. So for example, I could take as basis function 1 a basis function which has positive coefficients here and there. And as basis function number 2, I could take one which has a positive coefficient here, a negative coefficient there, and another positive coefficient, and so on. So I can collect all of these basis functions into a measurement matrix, and then I demand that the departure of my measurement matrix multiplied with this unknown function x, the departure from the observed signal be small. So in this particular case here with just two basis functions, I would have just two measurements, which would be the signal projected onto this black and onto the green basis function. And then I need a representation in a space in which a signal is sparse. For example, here this could be, so in this example 1, the measurement matrix would be a couple of peaks with a random sign, let's say. And psi in this example would, for example, be the Fourier basis, or if we don't want to deal with complex quantities, let's say the discrete cosine basis. If, on the other hand, so let's say the signal of interest, I will make it blue here in this plot to distinguish it from the basis functions. If, on the other hand, in my second example, I have a signal of interest which is sparse already, let's say my signal of interest had a peak here, and a peak there, and a peak there, then it doesn't make sense to use the same basis functions as before, because the chance of getting a non-zero inner product between my basis function and signal of interest would be very small. So the type of basis function that I want here will be very smooth functions. So for example, this would be a good smooth basis function, or one with a higher frequency. That would be a good smooth basis function. So the measurement matrix here would consist of very smooth basis functions. And well, the transformation, the original signal is already sparse in the original domain. So here I could use as transformation matrix simply the identity matrix. Okay, so what do we have overall? We have a term that makes sure that our reconstruction X explains the data. And on the other hand, I want this reconstruction. So the reconstruction should be sparse in some domain. Now this transformation here, rather than discrete cosine, let me say, in more abstract terms, that this would be smooth basis functions. Such smooth basis functions play nicely with a rough measurement matrix. Rough is not a technical term. So this works nicely. But using a smooth basis function and a smooth basis function both for the transform and for the measurement, that would not work well. But the identity is sparse, so the identity would work okay with a smooth basis function. So what one says is that the transformation matrix and the measurement matrix, they should be incoherent with respect to each other. Which means that the elements of phi are not sparse in psi, and vice versa. So what we have is that the solution lie within an elliptic subspace here, and the term in the objective function is also convex. So I have a convex objective subject to a convex set of constraints. So overall, I have a convex optimization problem. And if it's written as above, with the data term as a constraint and with the problem being underdetermined, this is called basis pursuit denoising. By its inventor Donohoe. And if you formulate it the other way around, and if your system is overdetermined rather than underdetermined, it is also called the lasso by Tibshirani and others. But really it's the same thing mathematically. It's called basis pursuit denoising here if this constant delta is greater than 0. If a delta is 0, so if delta is 0, then you just call it basis pursuit. I want to give a famous example for where this was used. And this famous example is single pixel imaging. This is from the lab of Baranyuk at Rice University. Above you see a sketch. So there is some continuous image which is mapped onto what is almost a mirror. But really, this mirror consists of elements that can be switched individually. And some of these mirrors, so let's say the white elements, will be adjusted such that the light coming from the scene is reflected onto this photodiode, whereas let's say the black elements, they are deflected, they just go off somewhere. And now the interesting thing is that we have a single photodiode. So we have just a single pixel. And the single pixel can now take multiple measurements. And because I can switch the elements of the mirror individually, this corresponds to masking my original image with whatever pattern I decide to use here for the switching of these mirrors. If you were to acquire, let's say this image of the photography here, this would be a rather, complicated way of acquiring an image. The rationale here, beyond showing that it's possible to get away with much fewer measurements than you would expect from Nyquist sampling theorem, the rationale here is that it is easy to build a camera in the visual, let's say, but for instance, if you have a camera that is to function in the infrared regime, this is much more complicated to build, at least in the far infrared, much more expensive. So there are wavelengths where it may be possible to illuminate your sample with illumination that is structured in certain ways, but where it is only possible to acquire measurements using a single photoactive element. down here a couple of examples. So on the left-hand side, a normal image of a black and white letter R was taken, and in the middle you see, so we have here 2 to the 16 measurements, and in the middle you see a reconstruction from just 1,300 measurements, which admittedly is worse, but it's interesting that you can get away with a comparatively small number of measurements and still see something. And then on the right-hand side, well, this was using a color filter in addition, and a total of 6,500 measurements. So this shows the principle where you overlay your image with your true image with a particular pattern. So you illuminate not the entire image, but you take the sum of the intensities that you can observe at all the green pixels. That was your first basis function. And then you next measure the sum of intensities that you have at the red pixels. This is the next basis function, and so on. So it's a kind of Monte Carlo integration, if you like. And these measurements are then used in the formula above. So the measurements are here in O, are used in this formula to estimate the true underlying signal, which in this case has a much higher dimension than your number of measurements. So the problem is strongly underdetermined, and you get a unique solution only thanks to this regularizing term here, which says that we believe that our image is sparse in some domain, where this domain needs to be somehow conjugate to the basis functions used in the measurement matrix. Probably the most relevant application that I've seen of this to date is in compressed sensing MRI, where you can really visit arbitrary points in K-space or in K versus time space, because they were looking at dynamical phenomena, and then reconstruct the full spatiotemporal volume from that. Or similar ideas are now used in limited angle tomography, there is, for example, a paper by Hu and Klofsky. They were looking at not all the projections that you would really need to get a full tomographic reconstruction, but rather they were looking at a very limited set of projections only. And then, thanks to these sparsity priors, we're still able to solve this undetermined problem and come up with very high quality reconstructions of the real image, thanks to the images being relatively simple. So this whole approach here relies on your being able to find a transformation into space in which a signal is sparse. Because, you know, if you don't, there's no way of avoiding making each and every measurement separately. So for example, if your image, if the underlying image is pure noise, and you want to measure this pure noise everywhere, so, you know, in this sketch here, I showed a signal which looks like noise, but it was sparse. I had mostly zeros. But if you have a signal like this, you know, where you have some value at each location, and there's no inherent smoothness or anything in these measurements, then it will not be possible to do sparse coding. But if you can find a transform in which your signal is sparse, then this works very well. The community has not yet quite agreed on what to call this, so it's sometimes called compressive sensing or compressive sampling, or sometimes it's called compressed sensing or sampling. I could not make out any distinction yet. To my mind, these are all the same. References. So the pioneers in the field are Dave Donahoe, who used to be at Stanford and then went for a stint in investment banking and then returned before the crisis. I think he's a super smart person, and I think he probably saw the writing on the wall and returned before it was, before everything crashed. Then there's Emmanuel Candes, who has been working on this, and some of the interesting applications come from the lab of Richard Baranyuk, who also maintains this very extensive web page here with hundreds of links to pretty much every compressive sensing paper, I have the impression at least, that has been written.